Alright, well, we're back to section 4.3. I'm continuing the example that we started in the last video. So we were examining the concavity around the inflection points and around the vertical asymptotes. So we had split up the real line into these intervals. We've got the interval minus infinity to minus 1, minus 1 to 0, 0 to 1, and 1 to infinity. So I'm testing key points in the second derivative. So f double prime of negative 2 gives us negative 12 over 4 minus 1, the quantity squared. That's ultimately going to be a negative number. And so that means that our function is going to be concave down from minus 1 to infinity. Next we look at the interval minus 1 to 0. So here I'm testing negative 1/2. F double prime of negative 1/2 is equal to negative 3 over negative 1/2, the quantity squared, minus 1, that whole quantity squared. And again, that gives us a negative number. We've got a negative in the numerator, a positive in the denominator. So overall, negative. So the function is still concave down on the other side of the vertical asymptote x equal to negative 1. Then we move on to the interval 0 to 1. So f double prime of 1/2, which is in that interval, gives us 3 over 1/2, the quantity squared, minus 1, the whole thing squared. That's a positive number. And so the function is concave up on the interval 0 to 1. And then lastly, we look at the interval 1 to infinity. We've got f double prime of 2 as our test. F double prime of 2 gives us 6 over 2 squared minus 1, the quantity squared. That's positive. And so we have our function as concave up, again, from 1 to infinity. Okay, so now I think we're ready to put all of this information together and get a pretty nice sketch of our graph. Let's go to the next page. Sketch in the coordinate axes. Alright, x-axis, y-axis. I'm going to sketch the asymptotes in green. So we've got the vertical asymptote at minus 1. That's a plus 1. We've got a vertical asymptote at 1 and at minus 1. Let me sketch those in. We've also got a horizontal asymptote, which I'll label in yellow, at 0. Okay, we found that. We know that there's an x and a y intercept at the origin, 0, 0. So now combining what we know about the intervals of increase and decrease and the concavity, we can go ahead and start sketching. So let's do minus 1 to 1 first. So on the interval minus 1 to 1, our function is increasing the whole way. It only crosses the x-axis in one spot, and the concavity changes at 0. The concavity changes from concave down to the left of 0 to concave up to the right of 0. So we've got to have behavior something like this. Okay. Now we think about what's happening to the right of x equal to 1. So what is happening on the interval from 1 to infinity? Well, we know that our function is decreasing. We know that we have to be approaching x equal to 1, either going to plus or minus infinity as we approach 1, because it is a vertical asymptote. And we know we have a horizontal asymptote at 0. We also know that the graph is going to be concave up on the interval 1 to infinity. So if we put all of these things together, in order to satisfy a decreasing function, in order to obey the asymptotes, and in order to have a concave up looking graph, we have to have behavior something like this. Okay, so the concavity is never going to change from here. Okay, it's always going to be a nice concave up smooth curve. And then similarly, if we look to the left of -1, so now we're looking from negative infinity to -1, we know that we always have a decreasing function and it's concave down. So since we don't have any other x-intercepts, we must have behavior like this. Okay, so now having all of these tools in our pocket from calculus, we should be able to sketch much more accurate graphs than we could from pre-calculus. So this was an example of how to sketch a rational function. This particular function, we didn't really have many critical points, so when you do explore an example with a lot of critical points, you probably want to see, is there a local min, is there a local max, what's happening around the critical point. So that's something to think about with some other functions that you might run into. This is just one type of function.